So, still lecture 8 slides, which I erased off the board. Okay, but these are still lecture 8 set of slides. For right now, I am going to skip talking about, and that's just for time reasons today, I am going to come back and talk about this. For right now, at the end of section 2, where we learned about K and Q yesterday, we can do some manipulating of equations and then manipulate K values, like multiplying them by each other or taking the reciprocal of them. Okay, this is manipulating K values. I am going to talk about this, but just not today. Okay, so I'm going to come back to that on Monday. Today, I wanted to go through section 3, which is this. Le Chatelier's principle. That's my best French that I can do, y'all. That's it. That's what I got. You know what I just call it? Le Chat. Yeah, it's just Le Chat's principle. Okay. I know, right? Le Chat's principle. I do, because it's so much fun, because I got a dance that we're going to do. Oh, okay. It's not really a dance. I'm being a little hyperbolic, but it's kind of a dance. Okay. We'll see if you should know. Everybody should probably know this dance from childhood. We'll see. Okay, y'all got this down? Le Chatelier's principle. Okay, so this is about when we do something that causes the equilibrium to have to shift. Okay, we are going to do something to make the equilibrium have to shift. Why can an equilibrium shift? Because it is not static, it is dynamic. Okay. So 13.3, Le Chat's principle, shifting. So I need you to, if you want to go ahead, I'm going to talk about it a little bit. I actually, for whatever reason, the last time I did this, I put these questions at the very end of your in-class examples. So you're flipping to the very last page. And this is where we're going to talk about Le Chatelier's principle. So like numbers 24 through 29 is what I'm really looking at, okay? So again, what we're doing is we're going to disturb the established equilibrium, okay? We're going to disturb the force, right? Mine says through 29, 24 through 29 on the back, right? Okay, that whole last page is this Le Chatelier's principle. Oops. Okay. Basic statement of this principle, if you need some words, is when you disturb the equilibrium, it naturally tries to get back to equilibrium. Okay? If you disturb the equilibrium, the reaction will try to get back. Okay? If we disturb the equilibrium, the reaction will try to return. It's going to get back to that equilibrium state by, and this is the word that we're going to use, shifting. Okay. It's trying to do what? Counteract what you did. Okay. It will return or will try to return? Does it always return? It always returns. Okay, if you want to write this stuff about Q and K, that's fine. I tend to think of this principle more in terms of comparing words. Not so much comparing Q values and K values here. Okay, so let's just think. We're going to have 1, 2, 3. Basically 3 ways that we can disturb the equilibrium. Okay. 3 ways to disturb. Let me list the ways and then we'll go through each one. Let's do that. 1, guys, we can change the concentration of reactants or products. Okay. Once it's at equilibrium, there is some of both in the container, right? At equilibrium, there is some of both, right? Okay. I can change how much there is of either one, and that's a disturbance. You okay if I just write reactants and products like that? R&P, reactants and products. Okay. I can change the volume of my container, and what specifically would changing the volume have an effect on in a reaction? I change the volume. Is that going to affect? Here's my container, right? I'm going to change the volume. I'm going to cut it down. If I have an aqueous solution in there, did me lowering the size change the volume of liquid in there? Sure doesn't. If I have solid, does me changing the size of the container do anything to that? Sure doesn't. You know that. Okay. But if I change the volume, what do I change? The pressure of a gas that's inside there. Changing pressure of gas is a disturbance in the force, the equilibrium. Okay. Where's my Yoda? Hang on. We will.
May the force be with you.
I know it's a huge shock to you guys that I'm a Star Wars nerd. I know that's like very out of character for a chemistry professor to be into Star Wars. I know. So again, changing the volume is really only going to do a disturbance to what? Pressure. Really, it's affecting the gases, right? Okay, it'll affect the gases. And then the third thing that we can do is change the, what do you think? Temperature. Which may change the state, right? It could freeze something, but you can change the temperature. All right. So when I change concentration, so here is what I need you guys to think of. Think about reactants and products as being on a balance beam. Oh, what is this? This is not what I meant. Seesaw. Okay. Again, this does not mean that the concentrations are equal, right? Okay. And that's not what I'm trying to illustrate here. What I'm illustrating is that the rate going back and forth is equal. Okay. So when they're at equilibrium, though, okay, here we go. This is the dance that I think of in my head. I don't actually think seesaw. I don't know why, but for me, I think about I'm a little teapot. You all know it. Short and stout. Here is my handle. Here is my spout. And when I get all steamed up, what? Hear me shout. Tip me over and pour me out. Okay. So when I'm doing this in my head, I'm like, oh, I'm a little teapot, and I'm going to tip. Okay. That's what I'm thinking of. Teapot. We are changing an amount on one side of the balance, right? Changing an amount. That's what changing concentration is. So let's do this. Y'all imagine with me. Yep. Do it. Hands out. You don't have to think you're a teapot. You can think you're a seesaw if that makes you feel better. So go ahead. That's fine. That's fine. Okay, what is always on my left side when I'm looking at it? Okay, this is my reactants. This side is my products. Okay. So let's first do the disturbance. Okay, let's mess it up. Let's mess it up by adding more reactant. Okay, so let's say I deliberately put more reactant into my mixture. How does that disturb my teapot, my balance? Okay, now I'm like this, right? Y'all hear what I said? What did I say? I added more reactant. Okay, so now I'm like this. How is my reaction going to shift? How does my teapot tip to get back to equilibrium? This way. You see how I shifted? What did I do? I shifted to the right towards products. Can we remember that with this physical motion that we're doing? No, that's not what I did. I added. Sorry, excuse me. Okay. If I add more reactant, the equilibrium shifts which way? No. Adding is my disturbance. How does the equilibrium respond? Shift to the right. The equilibrium shifts to the right. What if okay, do it again. Okay, so here's my equilibrium, my steady state. I got everything's in balance, and then I decide to disturb by taking away some of my product. Let's say I'm siphoning off some product, okay? Show me the disturbance that I just did. This side is less now, right? I'm siphoning away products, okay? So when I remove product, how does the equilibrium shift? Also to the right, just like that did. I did two different actions, but the shift result was the same. If I remove some product, it's going to shift to the right. Okay. Do the other two scenarios. All right. Here we go. What if I remove reactant? How am I disturbing it? Oops, now I'm like this, right? Which way do I got to tip? I got to tip to the left. My teapot's going to the left. That's how you want to take that. Okay. Why is it shifting to the left? I'm taking away some reactant. The equilibrium is trying to make up that reactant I took away, right? It's trying to recreate some of the reactant. What if I dump some more product into this reaction, okay? Here, now I have too much product. My equilibrium is disturbed. I've got too much product. What way is it going to shift? Left again. Because it's trying to what? Use up some product. I added extra product. Let's use it up. Let's do something with it.
So this happens the same with volume and temperature?
Nope. Just talking about concentration right here. This is just about concentration changes. It's only for this first change. Okay. If I do change the volume, Ooh. Okay, well, wait a minute. Let's double check. Look at 24 and 25. I'm not in class real quick. Look at 24 and 25. Okay. My first one, 24. I've got a reaction there. Here's the first one. What do you get if you add additional carbon dioxide to the mixture? Okay, well, where's my carbon dioxide? It's on the product side. Okay, guys, I mean it, like, just think to yourself, what am I doing? I'm adding more product. How will it shift? To the left, towards the reactants. You can use either phrasing. I go back and forth between saying towards the reactants or to the left, or, you know, I go back and forth, but either way. Y'all got that right? I can visualize my change. I can visualize my disturbance, and then I visualize the shift. Okay. God bless you. So yes, this reaction would shift back towards the products. No. Thank you. Back towards the reactants. Meaning, what would happen to my pressure overall of CO2 as it's shifting? Maybe should go down because it's shifting backwards. I'm getting less, you know. Okay. What about adding additional calcium carbonate? Let's say 2 different scenarios. Ooh, I'm going to get you guys. Y'all going to be so mad at me right now. Guess what? Let's consider it its own separate event. Yeah, let's say I'm just thinking about just in general. What if I add some more calcium carbonate? Can you guys write the K expression for this for me? You can write concentration or product base. I don't care which one. You write it. K. What is a K expression? K equals products over reactants, right? But what's not included in our K expressions? What's not included in a K or a Q expression? What is not part of figuring out the equilibrium constant? Solids and pure liquids are not part of calculating a value of K. Are they? K equals CO2 product is the only gas. These are both solids. Or, so that would be concentration based, right? Pressure based would be what? What's the pressure of CO2? And that's your equilibrium constant. That's your K value. Aha! Here's the thing with solids and liquids. This applies to liquids as well, okay? This applies to liquids as well. Pure substances, solids and liquids, pure substances. Do not affect the equilibrium as long as some of it is there. If it's part of the reaction, does it have to be present? Yes. There has to be some there. If it's not there, then your reaction is not going on. Okay? There has to be some there, but how much is there? Doesn't matter. There's no concentration value. How much is there? Doesn't matter. So adding more solid calcium carbonate does not cause this equilibrium to shift in any way. The equilibrium is established and that was it. Now, like we said, if I change the amount of CO2, does that make the equilibrium have to shift? Absolutely, yes. But not a solid or a liquid. 25. All right, here's a reaction. It's got all gases. Okay, so everything's a gas. So everything should, a change in the concentration or a change in the pressure should absolutely make the equilibrium shift. What if I remove some bromine gas from the mixture? Okay, do your teapot. What are you doing? I'm removing some bromine. If I'm removing bromine, which is a product, that means I'm now off balance this way, right? It's got to shift forward. It's got to shift right. Do the change described first, and then think about the movement that you make, okay? What if I add additional BRNO? This BRNO is a reactant, this side. If I add some additional, okay, now this side is too heavy, it's also going to shift right. Okay. All right, what about if we change the volume? I'm going to erase the concentration stuff, okay? Yes? Pretty good. Okay. All right, again, changing the volume is just going to change, it's just going to affect the equilibrium if there's gases involved, okay? It's only going to affect the equilibrium if there are gases. If there's no gases, then this has no effect, okay? All right, here we go. So now this is how we change the volume. What can I do with the volume? I can either increase it or decrease it, yes? So what if I increase, let's do decrease first. What if I decrease the volume? Okay, I'm decreasing the volume of the container. Let's do decrease first because I already wrote it up there. What are you saying should happen? Sorry, yes, sorry. I didn't know what you guys were saying. Yes, that is what's going to end up happening, right? If I decrease the volume, there is going to be an increase in pressure of all the gases, right? That's Boyle's law, right? From CHEM 1. Pressure and volume are inversely proportional. Okay. What does that mean about my equilibrium? What happens is, in this scenario, the equilibrium will shift to the side with other way. The least moles of gas. It's trying to even it out. It's trying to counterbalance. Oops, I manually increased the pressure in here. The reaction's like, well, let me back off to the side that has less gas so I don't explode. Yeah. Shifts to the side with the fewest, or fewer, I guess I should say, we're comparison. Fewer number of moles of gas. So does that mean left or right? I don't know. It depends on the reaction we look at, right? but the fewer moles is the preferred side in this scenario. And then so, of course, if we do the opposite, if I increase the volume, according to Boyle's law, that means what is happening to the pressure inside? Yeah, the pressure is decreasing. I got more space. I see a decrease in the pressure. So that equilibrium is like, well, hey guys, now I can just shift to the side with the most number of moles of gases. I can make a bunch of gas now. I got all this room. I constantly hear background noise, so I don't hear a loud cricket like in the room. So, I mean, there may be stuff going on. I don't know. Maybe it's a brain tumor, Loretta.
That's not funny.
I mean, maybe you have a tumor. It's not a tumor. You don't know that line? You don't know that reference? You don't know the movie Kindergarten Cop with Arnold Schwarzenegger from back in the day? You should watch that movie. It's fantastic. It's not a tumor. Me either. I need to show that movie to Kara Lee. Equilibrium shifts to the side with most number of moles of gas. What if each side has equal moles and I change the volume? Then there's no shift, right? There's no shift. If I have equal moles and I change the volume, there shouldn't be a shift because there's no preference. Look at 25 and 26 and 27. 26 and 27. Is that what I have up here? No, that was the first one. Okay, so there's an illustration in here about how pressure changing and all of that stuff. You can look at that if you want to. That's just Boyle's law. Okay. All right, here's a reaction. What if I decrease the volume of the mixture, the container? I decrease the volume. If I decrease the volume, pressure increases. Reaction, equilibrium will shift to the side with fewer moles of gas. My right side, my product side has 3 moles of gas, yes? My reactant side, mine has no gas. Okay, so if I decrease the volume of my container, this reaction is absolutely going to shift to the left, to the side with less gas. It's trying to alleviate that increased pressure we caused. Shift to the left. And likewise, if I increase the volume, if I give it more space, which side of the equilibrium is it going to shift towards? It's going to shift to the right. It's going to shift to the product side. Excellent. What about the next one? Here's this reaction. If I decrease the volume, which side is going to get shifted towards? How many moles of gas do I have on my reactant side? 3. Product side, I have 2. Okay. So if I decrease the volume, that means the pressure is increasing. It's going to shift towards the fewer side, which is to the right, to the products, forward direction, any of those words. Decreasing the volume causes this to shift to the right, forwards. Increasing the volume would cause the exact opposite, right? Okay. No. Again, if they are the same number of moles, then there's no shift, but that's the only special case. Not very. I mean, there may be. I may have intentionally picked an active question just to see if you were listening to me in class, but that's not very common. Huh? What? I wonder how well y'all were listening to me in class yesterday. I wonder if y'all know your bonus question on the test today. Nope, I'm not telling you nothing again. I actually talked about it twice yesterday. No, I talked about it twice yesterday, and you were here for one of those times. Yep. What I talked about yesterday, guys. You know my bonus questions are always about me. I told y'all some stuff about me yesterday.
I will copy in. Just talk of no bonus questions.
Okay, last one, last change we can do. Temperature. To judge this change, we need to know if a reaction is absolutely endothermic or exothermic. How do we know that? Usually, what's one of the things, a piece of information we're given to know if it's exothermic. If the reaction is, which one do I want to write first? Endo, let's say that first. If the reaction is endothermic, I don't know if this is what matches with what's on the slide right now. Just look at what I'm writing here. Okay. Endo. That means the delta H, if you're given a delta H, the delta H value would be a positive number. Okay. Another way you could see this though, endo. What does endo mean? Absorbs heat. You could see an endothermic reaction written maybe this way. Maybe I might the word heat on the what side? Yeah. On the reactant side. Heat has to be added. You saw that, you should know that means it's an endo reaction. Okay. All right, so if it is endothermic, if you increase the temperature, the equilibrium will shift. And now we can go back to thinking about our teapot here, okay? Let's think about our teapot. What is the disturbance I'm doing? When I increase the temperature, I am increasing the amount of, yeah, but in this context, I'm increasing the amount of heat there, right? Okay. So if I'm increasing the amount of heat, the disturbance I've done is, right? How will the reaction shift to get back to equilibrium? Right. To the right. What if I decrease the temperature for an endothermic reaction? What am I doing? I'm actually getting rid of some of the heat available to it, aren't I? There's not as much heat available. So what have I done to my scale? Uh-oh. Not enough heat. So what way is the equilibrium going to shift? It's going to shift left. It's going to go in reverse, right? It's going backwards now. Oh, why not use a totally different color? I'm going to be very colorful today. Let's see. Describe think about what will happen if it's an exo reaction. If it's an exo reaction, it's like the exact opposite of all of this. Yes? If it's exo. If you're given a delta H value, then that means that delta H value is a negative number. If you're just thinking about heat on the reactant or the product side, for an exo reaction, where is heat? Yeah, it's a product, right? Isn't heat given off? You think of heat as being on the product side. So if you increase the temperature and it's an exothermic reaction, too much, shift left. Increase the temperature in this scenario. I don't know what I was trying to say. Scenario. Let's say scenario. Situation scenario. Increase T, it shifts left. If I decrease T, I get rid of some of the ambient heat around the reaction. I decrease the temperature. Man, that reaction is just going to go so far. It's going to just keep trying to make that heat up so far to the right. Good deal. Look at the last two on that page, 68. I don't know, y'all. No. 28 and 29. Okay, the reaction is endothermic. This reaction is endothermic. Okay, so I'm telling you it's endothermic. Again, you could think of it being endothermic as writing heat as one of the reactants. I do that all the time. That's how I think about it. Okay. So if it's endothermic and I increase the temperature, which way should it shift? Towards the products to the right. Yes. If I decrease the temperature and it's endothermic, I'm making it go in reverse. I'm sending it backwards. I'm sending it to the left. It's exothermic. Heat is on the product side. I increase the temperature when it's an exothermic reaction. The equilibrium is actually now going to go backwards to the left, yeah? But if I decrease the temperature, an exo reaction is going to go forwards to products. Very good. Very good. Okay. And then I want to show you guys how to do just some. We're not going to get into all of it today by any means. Some of the math with equilibrium calculations, okay? There you go. I thought that might be encouraging to you guys today for some reason. Yeah, today of all days, I thought this would be the encouraging day to share this with you. This is a very good day to share this. Oh, I saved it in a folder. I'll do it at some point. Okay, does everybody have, so this is new set of lecture slides now and a new section that we're starting. This is actually the last section of this chapter. Chapter 13 only has 4 sections. I know. No, because I'm doing 2 chapters on this test. 13, 15. Oh, well, then we're coming back to it. And 14 is its own test. Because 14 is huge. Acid and base equilibria. We gotta learn a lot of stuff about acids and bases to do that, Jeff. Okay. So, again, this is a new set of slides now. This is lecture 9 slides. Section 4. How do we do equilibrium calculations? Using Miss Poe's typed up guidelines to how to solve equilibrium problems. Okay, so this paper, so this would be what, lecture 9, right? Yes, okay. I mean, the idea is that you're going to practice enough, you don't need to write it on your note card. Right? Right? No, y'all don't need this on the test. You're going to have enough practice with it. So, Miss Poe's Guide to Equilibrium Calculation. So, I basically think about equilibrium problems as one of 3 types. Okay? They basically fall into one of 3 categories. Easiest one, let's look at that first. The easiest type is what I call type 1. I don't know that you would ever find another professor who does it this way. Maybe, I don't know. This is the way my brain organizes this kind of information, so this is what I teach you. If I have a type 1, what Poe calls a type 1. This is the easiest type because it is essentially just plug and chug. You guys know what I mean when I say that, don't you? You have a formula and you plug in the numbers and you solve for the thing you don't know. That's it, right? You plug and chug with your K expression. This is the easiest type. What do you have to have in your K expression? Just any concentration at any point in time, or must be the concentration when the reaction is at equilibrium? This is when you are given, right, concentrations that are already the equilibrium values. You're told in the problem, at equilibrium, the concentrations are blah. If you are given all of the equilibrium values already, can you solve for K? Can you write your K expression from the equation and solve for K? Yes, absolutely. That's one type. That's a type 1. That's a type 1. Look at number. We did this yesterday, right? 2B. Didn't we do 2B yesterday? Look at 2B on our things. Didn't we do this exact thing yesterday? Given the equilibrium concentrations, solve for K. Sure did. Look at number. Nope. Look, 15. Let's read 15. Now I gotta find out on the slides. Nope. Here we go. Read through the question. Yeah, it's got a lot of words. Yeah, it's describing a lot of stuff. I don't care. You can pick out what the numbers are. Right? Yeah.
2,000 degrees Celsius.
What's given to us here on number 15? What's given to us? What are we given?
We're given 1 pressure, 1 2 temperature.
The very second sentence, it says, at 2,000, the value of K is, okay, that's something I was given, right? I was given K equals 4.1 times 10 to the negative fourth, yeah? What else was I given? What am I asked to find? Calculate equilibrium concentration of NO. Okay. Calculate equilibrium concentration. The concentrations of N2 and O2 at this pressure and temperature are, here's this molarity. This is applying to the N2, right? That's why I say respectively, yes? This first molarity is N2 and this second molarity is O2. And these are the concentrations at which point? I say these are at equilibrium, right? No, O2, not H2. What am I solving for? Calculate what? Equilibrium concentration. So I want the concentration at equilibrium of which thing? NO. Guys, tell me what you have. You were given K. You were given all equilibrium concentrations except one. And that's the one you're solving for. What do you have to be able to do first? Write your K expression. Using what as your guide? Overall balanced equation. In the problem, what was the balanced equation given to you? N2 gas plus O2 gas makes, in equilibrium, 2 moles of NO gas, right? What is K? If that's your equation. And I'm using concentrations here, so I'm specifically finding KC, but that's duh, okay? That's what we have is concentration. So products over reactants, right? Concentration of NO raised to the what power? 2 squared divided by what? N2 times O2. And both of those are to the first power, yes? How do I solve for just NO? Multiply both sides by the bottom and then square root it. The concentration of NO at equilibrium is equal to the square root of K times the N2 concentration times the O2 concentration. Plug and chug. Yes? Yes. Plug and chug. Yes. 3.6 times 10 to the negative fourth. Now, I was bad here, and I would lose a point or a half point because I didn't put something with my answer that this answer has to have. Because I'm calculating a concentration. K is unitless, yes. K, Q, no units. Concentrations are not unitless. Molarity. Badness Poe. Minus 5 points. Type 1. Type 2, and then we'll stop. And I may only get to do one example of type 2, and then we'll pick up more on Monday, but I want to show you this. Okay. Okay. When I type 2, the way I describe a type 2. Goal. Calculate K. So in a type 2 question, that's usually what's being asked. What is the value of the constant? What is K? What is the value of the constant? What is K? You are going to be given at least one initial concentration. And then you're going to be given at least one equilibrium concentration. Okay? This is how you're going to recognize a type 2 problem. Yes? I'm looking for K. They gave me an initial, and then they gave me an equilibrium. Okay. This is what Ms. Poe calls a type 2. Okay? We got to use this thing called an ICE table, or sometimes they're called rice tables. I say ICE table. Okay? We're going to organize our info into what is this ICE table. This is a very standard way to do this kind of problem. This is how we keep track of our information. This is what the chemist does. What does ICE stand for? I, baby. Yeah, it stands for ICE, baby. Initial, change, and then equilibrium. If your teacher talks about the R for the rice table, it's because we're going to write the reaction at the top of the table. Okay. But I learned it as an ICE table, so that's what I say. The best way to learn this is to do one. Just know that this is how we're going to organize our information. ICE, initial, change, final. Look at number 12. 12 and 13 are both what I consider to be this type. So we're just going to work one of them right now, and then, wait a minute. My numbering's off. It's not 12 and 13. Sorry. Hang on. Because I think it might be 17 and 18. It has the table already drawn for you guys. Is that right? Okay. No, you're fine. So you guys might want to actually change. Okay, so change. You see on here on Poe's guide that I listed some question numbers to go look at. Okay, so let's change. So when I talk about a type 1, and it said look at number 2B and number 3, those are correct. Where it says numbers 14 and 15, mark those out. 15 and 16 are type 1. 15 and 16. Okay. So just mark out 14. Yeah, and add 16 to that. Okay, and so then type 2, which is what I'm going to show you guys, it says C examples 12 and 13. Scratch those out. C examples 17 and 18. Oh, yeah, okay. You're fine. Fine. You're fine. The quadratic. Yeah, that's Monday. We'll talk about that on Monday. We got to use the quad. We got to solve a quadratic. Oh my God, y'all are fine. Just chillax. Just chillax. No. It's easier than you'll think, I promise. Okay, let's do 18 together. 17 is very straightforward, but let's do 18. I like 18. Okay. So again, read through 18 and see if you recognize the clues that I said look for. Let's see. Is it asking us to calculate the equilibrium constant K? It's the very last sentence. Calculate the equilibrium constant. Okay. Are we given at least one initial concentration? When 1 mole of each of these is allowed to react with 1 liter, that's an initial concentration. Okay. That's an initial concentration. Okay. Equilibrium is established when 1/3 of a mole, or 0.33333, okay, moles of each reactant remains. Is that not at least one equilibrium concentration? This is a type 2. Okay. So what Ms. Poe says is a type 2. So if it's a type 2, what's the first thing you will write? I wrote it for you here, but what's the first thing you guys are going to write? Yeah, you're going to create an ice table. ICE. This is a table. Above the table, you write your reaction. What do you guys see there as a product? I'm going to be easy for myself, and I'm going to write these as A and B. Okay, I'm just going in the same order as these are. If you want to write A, B, C above them for yourself, that's fine. Okay, and then there's my equilibrium arrow is going to make C. And what about water? What about water here in this problem? It says it's a solute. It is not a pure liquid here. So it counts in my K expression. It is not a pure liquid. It's not a liquid, so it counts. Okay. It is part of the K expression here in this reaction because it is not a liquid. It is a solute. It is dissolved in something else. Initially, all of these are concentrations, right? Initial concentration, equilibrium concentration. What's the concentration of that first reactant, the C2H5OH? How did y'all get that? Remember, when I say a concentration, it is moles per liter. So this said you just have 1 mole, and it said you just have 1 liter. It just said actually 1 and 1. But what if you had not 1 liter? What if you'd had 0.5 liters? You would need to do 1 divided by 0.5, right? That's the number that goes here. The concentration goes here. We can just say 1. Okay, 1 molar. What about my other reactant? What was its initial concentration? 1 molar as well? Initially, before the reaction happens, do you have any product? You do not have any product initially unless it tells you there's some there initially, right? Okay, let's talk about the change. I don't know how much it changed yet. That's kind of the whole point. I don't know by how much it changed. It just changed by some amount. The amount that it changes by, since we don't know what it is, we use the letter X. I don't know what this number is yet, so it's an X. Should this and this, A and B, both change by the same amount? What is their mole ratio? 1 to 1. Guess what? We've put the coefficient as a multiple of the change. If it was 2, the change would be 2x. If it had a 3, the change would be 3x. How do reactants change over time? They get smaller, which means their change is a negative value. Okay, let's think about the product side. By how much is this change? We're still going to use X. Is this going to be the same amount of change as these other ones? Isn't this all 1 to 1 to 1 to 1? Yes. But on the product side, this is a positive change. It is increasing by that amount. At equilibrium, then, what is the concentration at equilibrium? Initial and the change. Initial minus the change. This plus this. That's why we put a negative sign here, right? And that answer will be molarity, yeah? A lot of times, guys, I'm going to not even write the M symbol in the table. It just takes up more space, okay? It's concentration. It is molarity. We all know this now. So a lot of times, I won't even write the capital M there anymore, okay? What is this equilibrium concentration? Also 1 minus X. What is C's equilibrium concentration? Just X. 1X, just X. And D, or my water, also just X. What do I say to do next? Method. Fill in ice table. That's what we just did. Write the K expression. What's my K expression? Products over reactants. Including water in this problem, because water is not a liquid here. Okay. All of these have an exponent of 1, right? What do I know needs to fill into these brackets? The equilibrium results from my ice table. These algebraic expressions represent the equilibrium concentration of all 4 of these, right? The algebra term. What's on the top? C at equilibrium is an X. Water at equilibrium is also an X. A and B at equilibrium are also both 1 minus X. This is not negative 2X.
Oh, wait, no. Oh, yeah.
Yeah, okay. This is not negative 2X. 1 minus 2. No. But guess what I know from the problem? What did I know from the problem? I said you have to be told you're solving for K. You have to be given initial of at least one thing, and you have to be given the equilibrium concentration of at least one thing. What was I told the equilibrium concentration of? Each reactant at equilibrium is what? A third of a mole in 1 liter, isn't it? What's that molarity? 0.33 repeating molar, right? That is the equilibrium concentration. Does that mean I can solve for what X is now? Yes. If the concentration of A at equilibrium equals 1 minus X, according to my chart, it's 1 minus whatever the change is, right? And then at equilibrium, I'm telling you that that number's got to equal 0.33. What is X? .67, 0.66666666. Yeah. That's the amount of change that happens in this equation. How much does A change by? That amount. How much does B change by? That amount. How much does C change by? That amount. What if it said 2X? How much would it change by? That amount times 2, right? That amount times 2. So you know what X is. Plug in and solve for K. Can you think of that as 0.67 squared? Yeah, that's what it is. What is each one of these? 0.33, right? 0.33. Each one of those reactants is 0.33. What is K? Oh no! I know. What is K? No units. And no units on K. All right. That's a type 2. And we'll talk about type 3 with the quadratic on Monday. But you guys are going to go ahead and start your first homework set for chapter 13 because it has the first 3 sections. So the things we talked about yesterday plus Le Chatelier's principle. The equilibrium problem set, I'll open it and you could probably get through the first few with just type 1 and type, or go through and try to identify anything that is a type 1. Let's try to do it. Anything that's a type 2, you can try to do that, right? Okay. So you're going to be working on chapter 13 homework over the weekend. I also have for you guys a lab worksheet over equilibrium. This is not going to be due on Monday when you come back. I mean, it'll be due, it may be Tuesday or probably Wednesday, because some of these problems, yeah, are the type 3. Okay. But y'all have this. Again, don't save it until Tuesday to do. Work on some of it this weekend. Okay. So I'm going to set that up here. Be sure you grab it on your way out when we're done with the test.